This video is going to discuss higher derivatives, and by higher derivatives it just means taking another derivative after, say, the first derivative. So here we might begin with an original function, okay, and then we probably have seen the first derivative, f prime of x, which we could also represent as df dx in this case, using Leibniz notation. Now, after that, if that happens to be, so we have to have it exist so we can find the derivative, and it exists on an interval, okay? And on that same interval, if we're able to differentiate it again, so using our same tools and techniques for differentiation, we can get the second derivative, okay? Second derivative, I could also represent this in Leibniz notation as d squared f of dx squared. And this is just notation, but what this means is, okay, well, this, I can technically write this as d dx of f of x. And all this means is that, okay, well, you have the derivative, the first derivative, let me rewrite that. We have d dx of f of x, okay, and that was the first derivative, but we're actually taking a derivative of that derivative, and so they chose to consolidate the notation and say, okay, well, d times d is d squared, and dx times dx is dx squared. This is just a notation thing, okay? So don't get thrown off. We're not doing any exponents. We're not doing anything like that. This is just notation, so just notation. And then similarly, so that's the second derivative. Typically, we only do two of them. We can choose to do more. In real-world situations, two is generally all that's really significant to us. However, we can keep differentiating. Again, assuming that the derivative exists, I can take a third derivative. And so this would be the third derivative, and notationally, again, this would be d cubed of dx cubed, and then I would put the f in the numerator. Okay. Again, just notation. Again, it would be, this would be, we'd have three sets, so d dx of d dx of d dx of f of x to, let's see, closing, closing, and closing. Okay, something like that. Okay, just notation. And so in general, I can keep differentiating, find the fourth derivative, and go on, and I can take the nth derivative. I can keep differentiating till my heart's desire, and probably at some point we get a constant, and everything after a certain point is zero. Okay, so again, the idea, we generally will probably stick to the first two derivatives, but we can keep going if we wish. Okay, so just a quick example here. I want to find f double prime of x if that's our function. Okay, so if I look at the derivative f prime, this is equal to, okay, by the power rule, for the first quantity here, 4 times 2, so let's just write that as 8, 8x cubed. Okay, and then the second part, okay, this is a product rule, so 1 and 2. Okay, so it'll be, let's see, 1, 5x squared, times the second, so times the derivative of the second is 1 over x, plus 2 d1, so 10x. Okay, and I'm just going to clean this up a little bit. 8x cubed, distributing the minus sign and simplifying at the same time, minus 5x minus 10x ln x. Okay, and then I can go ahead and differentiate again a second time. Okay, derivative of 8x cubed, that is going to be 24x squared, derivative of 5x, negative 5x is minus 5, and then this again is a product, so 10x times 1 over x, if it'll let me write. Okay, and then so that's 1d2 plus 2 d1. Okay, and again, just for my own sake, I'm going to clean this up a little bit. This will be 24x squared minus 5, distributing the minus and simplifying here. This is minus 10, and there should be a plus in there. Minus 10 ln x, and so this is going to be 24x squared minus 10 ln x minus 15. Okay, and again, that's just differentiating a couple different times. Okay, so we found the second derivative. Now, higher derivatives come into play specifically in physics. Okay, so if we have a position function, which is s, okay, the velocity is given as the first derivative. Okay, and acceleration is the second derivative of position. Okay, and this, again, there's certain assumptions that go along with this, so we have to have a nice smooth position function, and I mean, this works in some cases, and in most theoretical models it works. In reality, it can be a little bit different. Okay, so just an application problem to consider is we have an object in free fall. We assume that air resistance is negligible, and so position is measured in feet and time is measured in seconds. And we're given an equation below, and we assume that positive direction is down. Okay, and so what we want to do is determine equations that model the object's velocity and acceleration. Okay, and then there's other questions to go along with this. Okay, so if I go ahead, and so I know v of t, so velocity, is the derivative of position. So if I take the derivative of this, I believe, okay, 15, that's a constant that differentiates to 0. Derivative of minus 2t is minus 2. Derivative of 16t squared is plus 32t. Okay, so that is the velocity. This is a function that gives the velocity at time t, and the units for this would be feet per second. Okay. Similarly, acceleration is the second derivative of position, so meaning that I have to take the derivative of the velocity function that I found, which is just 32. Okay, and this would be acceleration at time t, and the units for this would be in feet, and then per second, or feet per second squared. Okay, you can double check the unit algebra on that one. Okay, now I answered the first two parts, but I read the question and I have another part to answer. So when is the velocity equal to 0? Okay, well, okay, set the velocity equal to 0. Minus 2 plus 32t is equal to 0. Okay, solving that, I get t is equal to 1/16 of a second. Yep, 1/16 of a second. Simplifying and all that stuff. Okay, so what this means is that at time is equal to 1/16 seconds, the object is not moving. Okay, so the distance is not changing. The object is not moving, or the position is not changing. Okay, so this is an example of one type of extension question that we can ask you in addition to finding those functions. There may be other ones too. We might ask you, when is the object not accelerating? Okay, so that would be set the second derivative or set acceleration equals 0. just make sure to read the questions carefully in there and make sure you answer all their parts.